In this lesson, we're going to talk about passing uniform data to shaders. So let's expand lesson 3.2 in your project, in your solution, and set it to the startup project. The program.cpp file is identical to the previous demos, and rendering game.h is similar, but there are a couple of additions that I want to point out. First, we're actually going to use the first-person camera class this time around. In the previous demos, we've just been rendering in screen space. We've been rendering directly to the screen in screen coordinates. Now we're going to start using object space and transforming those into screen space, using the mathematics that you learned in lesson 2. So we're going to talk about the first-person camera, how that is involved in the process. There's also a new class called Grid, which we'll get into, and instead of our colored triangle demo, we've got a cube demo class. And our rendering game class looks very similar to before. We still set up our camera at our keyboard handler just as we did before. We're instantiating a grid and a cube demo and adding them to our list of components. Now we're actually setting the camera. This is a little bit different. We're setting the camera this time, and you'll see why here in a little bit. Just so that it's set 5 units above on the Y and 10 units back on the Z, and then we rotate it pitch 30 degrees down, and you'll see where that comes into play here in a bit. And the draw method is a little different as well. And in this time, not only are we clearing the color buffer, but we're also clearing the depth buffer. So we call GL buffer FE again, just like we did before, but this time we specify the enumeration as GL depth, and we specify the value 1 that we're going to set this to. Now, I had mentioned the depth buffer before, but I want to focus a little bit on it now. The depth buffer is necessary because the same pixel can be rendered multiple times in a scene, in a single draw call or in multiple draw calls. The way that the depth buffer works is that objects or pixels that are behind another pixel won't be rendered to the screen. They'll be called. That's the Z test, right? The calling test, the depth test. The value 1 in the depth buffer specifies the farthest that the pixel can be away from the camera. And the nearest that the pixel can be to the camera is 0. Anything that is greater than 0 and less than 1 is possible to be rendered, but if the thing that you're trying to render is greater than what is already in the depth buffer, it'll be discarded, won't be written, because it'll be behind that pixel. So we're going to clear the depth buffer. Now, what is the depth buffer? What does it look like? What is it made up of? Well, it's a 32-bit buffer just like the color buffer is, but instead of storing colors, it's storing depths. And we can define different precision for that. We could have 8-bit depth or 16-bit depth. Most commonly, it's a 24-bit depth. And we're using that 24-bit value commonly to specify how much position and where is this pixel with proximity to the camera. Okay, let's look at the cube demo because that's where most of our code is going to be. And our cube demo, open up cubedemo.h. And take a look that cube demo has very similar data here, our vertex attribute position, our vertex attribute color. In fact, if we look at our cube demo vert shader, our vertex shader, it's almost the same as the lesson 3.1 shader, right? The same layout data, right? We still have a position, we still have a color, the same output via struct. The out.colors is almost the same. The one difference is, instead of just passing through the position to the GL position variable, now we're transforming it by the worldview projection matrix. And you'll notice the worldview projection matrix is marked with the keyword uniform. It's a mat4, which is a different variable type you haven't seen yet. Just like we have vec4, mat4 is 4 vec4s, right? It is a matrix, a 4x4 square matrix. And we're going to call this one a worldview projection to denote that it is the concatenated matrix of the projection matrix, the view matrix, and the world matrix. But the layout of the vertex buffer is the same. So a lot of similarities to what you've seen before. Just now, instead of the data already being provided, the position data being provided in screen space, the position data will be provided instead in model space. It needs to be transformed into screen space within the vertex shader. Let me drop this out here. That's an extension that we'll add in a minute. The shader program is just as we've seen before. And we have a vertex array object and our vertex buffer just as before. We have a few new variables that I want to talk about. An index buffer. So far, we haven't talked about indexed data. All of the vertices we specified for our single triangle last time were specified 1, 2, 3 vertices. We specified all 3 of them. An index buffer allows us to specify a smaller number of vertices and then specify an indexes into those vertices. Let's use the example of a cube, and you'll see this here in just a second, where a cube could actually be made up of 8 total vertices. Right? If we look at our cube demo, I'm going to foreshadow here just a little bit. There's actually 8 total vertices. If you can envision a cube right now in your head, 4 vertices to make the quadrilateral for the front face of the cube, 4 for the back. Well, those would be duplicated over and over and over again for each of the triangles and unnecessarily duplicated. So we can use an index buffer to reduce the duplication. I'll get into that a little bit more here as we progress. Now we have a GLint for the worldview projection location. This isn't the matrix itself. We're going to store the matrix in a GLM mat4 object on the application side called mWorldMatrix, and we're going to use this GLM mat4 and pass that matrix into the vertex shaders worldview projection matrix. Okay? This guy, however, is the location of where this thing is in the vertex shader, because we can have multiple uniform variables inside of the vertex shader or pixel shader, fragment shader for that matter, and we can look them up. We can look them up by their name to say, which one am I talking to? And that's what that location is all about. So now let's dig into the implementation of our cube demo. And notice that let me hop back over here just one comment down. There we go. So if we hop back over here and we look at the implementation of the cube demo application, same code as before, right? We want to compile a vertex shader and a fragment shader. And now we're going to build a vertex buffer, and this time it's still vertex position color objects that we're creating. I've assigned 8 unique vertex colors for each of the vertices. And imagine a cube. That cube then is going to be made up of 36 indices, a whole set of triangles, right? So each of these triplets specify one triangle, right? So this is the front face and the second face, third face, fourth face. All 6 faces of the cube are specified with these 36 indices. Those indices point into the vertex buffer, so to speak. The 0th index here refers to the 0th vertex here. 2 refers to this vertex. 1 refers to the index at element 1. Now, the idea of those index buffers is that I can pass in a smaller set of data. This is still unsigned in, so this is 32 bits per index. But I could have specified shorts because this is a fairly small index buffer. I don't need an unsigned int. I don't need 32 bits to store all of this data. Frankly, I could use a byte to store this index data. But the idea here is that I can specify a much, much smaller set of data than duplicating all of these vec4s and colors over and over and over again for 36 vertices when 8 will do. Passing smaller amount of data to the GPU over what's called the graphics bus is always a good idea. That's very commonly a bottleneck between the CPU and the GPU is the graphics bus. So if we can reduce the amount of data that we transfer over it, all's the better. Just as before, we've got GLGen buffers for a vertex shader, bind buffer, and then buffer data calls to populate that data. Same thing for GLGen buffers for the index buffer. GLBind buffer, this time the target that I'm using is GLElementArray buffer, which says these are the indices. Instead of vertices for GLArray buffer, this buffer we use to store indices. And we'll pass in the indices array into that index buffer. This is the same code that we saw before. This is the vertex array object creation, binding vertex attributes. What's new now, though, is the lookup into GLGetUniformLocation. And GLGetUniformLocation asks the shader program that we've already built and linked, where is the worldview projection uniform? So it uses that string to find that same string here inside of the vertex shader in this example. And it's going to find it in the vertex shader. It could be anywhere in the program, and it's going to find its location. And if that location is -1, then we didn't find the uniform location. And I'm going to say that that's an exception because I'm going to guarantee that that's found here. We're going to use that worldview projection location as input into the call to GLUniformMatrix for FV. So if we look at the draw call is going to look very similar to before. It's GLBind vertex array to bind the vertex array object again. Bind buffer this time twice, one for the vertex buffer, one for the index buffer, the element array buffer. We use the program that we've built. And now if we look at this call, this is the call that's really different. We're saying for the worldview projection matrix, get the view projection matrix from the camera. And I'm going to dive right into the camera here in just a moment. Multiply it by the world matrix, which the world matrix at this point has been initialized. We can go back up here and look at the world matrix. It's this default initialization. So that default constructor for the world matrix actually produces the identity matrix. That's part of the GLM's behavior, is that the default CTOR for the GLM mat4 is the identity matrix. So really, without modifying the world matrix at all, the worldview projection matrix is really just going to be the camera's view projection matrix. I'll explain that here in just a moment. GL uniform matrix 4FV. So I want a 4x4 matrix. I'm going to pass in to that location, right? How many do I want? Just one. Do I want to transpose this automatically? Let's say that this was not in column major format, but it was in row major. I could transpose it through the API. And then the array of 16 floating point values. This syntax here, ampersand, WVP, bracket, bracket, that's part of the GLM overload. So GLM has operator bracket, bracket, basically just says, give me a single floating point value to the start of these 16 floats. So that's what sends the worldview projection matrix to the vertex shader. Now the next two calls I want to talk about, I've got a GL enable, GL call face, and GL front face. Now GL call face, this specifies calling. This is by default turned on, so we automatically call clockwise triangles. What I mean by this is triangles have two sides. They have a front side and a back side. The front side, and this is with respect to the camera, so the front side is what's typically visible. We can't usually see the back side of a triangle. We would only see the back side of a triangle if it was an incomplete object, meaning that we could see inside of the object. Maybe we had cut the cross section of a teapot, and we could see inside of the teapot. Well, if we had calling turned on, and those otherwise back-facing triangles were called out, they would be invisible. By default, the front face, which is specified with the GL front face, the front-facing triangles in OpenGL are counterclockwise. If you inspect some of these, where their positions are in object space, you'll see that these are actually counterclockwise for the front faces. If I specified it the other way around, and I can do that as we render this, but it would look odd. The front faces would be called and the back faces would not. Finally, the last call here for the draw call, and I'm going to get into the camera here in a moment, I promise, but the GL draw elements call. This is different than GL draw arrays. GL draw arrays is an unindexed draw call. GL draw elements, I'm still specifying GL triangles, but this time I'm specifying that I want 36 indices that I want to process. And those 36 indices will make up these faces. And I'm going to specify their data type as GL unsigned int. So that's exactly the data type that I specified here. If I had GL shorts, then I would specify GL short here. And 0, where am I going to start at? I want to start at the 0th triangle. So now I'm drawing not unindexed data, but indexed data. That data will come into the vertex fetching stage from the GL element array buffer. And then again, we unbind the vertex array object to make sure that nothing else modifies our vertex array object without us knowing about it. Before I look at the camera, I just want to show the output of this code. Okay, so there's a couple things to note here. The first is, there's our cube, right? So there's our cube, and you can see how each of the individual vertices has got a different color. And if we look at the vertex data, we've got green and yellow and white and blue, and there's green and yellow and white and blue. And we can also see that this is set on top of a grid. It's a three-dimensional grid just in a 2D plane. And that's just what I call a reference grid, and I'm going to show you the code to render that. And I've also got a camera that I'm moving around with first-person shooter-style controls. So I'm using the W key to go forward, the S key to go back, and the A and D keys to strafe to the left and to the right. And I'm using the mouse click, so this is a left mouse click, and moving the mouse around to get pitch and roll, right? So this is pitch, and this is yaw. So that's the first-person camera. The vertex shader transformed all of these -1, 1, -1 first into world space, and then into camera space, and then into projection space to be displayed onto the screen, rather than directly into screen space as we had hard-coded the last two demos. So I want to mention the fragment shader as well. This fragment shader is identical to the previous one. All we're doing is taking the input color and producing it at the output color, and you saw the interpolation in practice there. So now let's look at, in our cube demo, we've got a camera, and our camera's output is this view projection matrix. And the camera was actually specified when we instantiated the object inside of our rendering game class. We specified the camera as a first-person camera, and we passed it to our cube demo class in its constructor. So what does this look like? Well, the short answer, let's look at the class declaration first. First-person camera is inheriting from camera. And I want to talk about camera first, so then we can talk about the first-person camera. So The camera class is a game component, so it's not a drawable game component. It has no rendering per se. And it has a couple of constructors, one which accepts a field of view, an aspect ratio, and a near and far plane. Recall back to the discussions from lesson 2, where we described a view frustum as made up of these components: a position, where does the camera look, which way is up for the camera, and then things like the field of view, aspect ratio, near and far plane. Those are the elements that go to make up our view matrix and our projection matrix. Those are the outputs. The view matrix and the projection matrix are the outputs of our camera. And notice then that that's the data that we have stored here. We have a field of view, aspect ratio, near and far plane distances, position, direction, meaning which way is the camera facing, what am I looking at, so to speak, which way is up, and then this right vector is an orthogonal vector between the up vector and the direction vector. So the right vector is orthogonal to those other two vectors. And in fact, it is computed as a cross product between these two vectors. Finally, we store the output. Every time we want to update our camera, we're updating the view matrix and potentially the projection matrix. These are the outputs of our camera. And these are just accessors. So we have position, direction, up and right, and aspect ratio, and just the accessors to that private data. And the view matrix and projection matrix, those are constant references for those matrices. And the view projection matrix is actually a concatenation of those two individual matrices. And finally, we have some setters there and the ability to apply a rotation to the camera as well. Reset sets it back to some reasonable values. Position is 0 and up is the y-axis and things like this. So let's look at the implementation here. Now that you understand a little bit about what the structure of our camera is in code, let's look at some of the implementation. So our first constructor just takes defaults for all of the field of view, aspect ratio, near and far plane distance. You can modify these defaults to as you see fit, or the end user can specify those 4 values. Most of this code is just accessors, right? Simple accessors or mutators to set position in this example. In reset, I had said, let's reset these to some reasonable values. I have a helper class called vector3helper, and vector3helper just defines things like what is 0, all zeros for a vector 3 and 1, and forward and backwards, up, down, right, left. Just some simple things. This is true for vector 2 and vector 4 as well. There are a couple of helper classes that I think you'll find helpful. Back to camera.cpp. Now, inside of the initialize call, its job first is to update the projection matrix. Remember, the initialize is typically going to happen for this component just one time. Update projection matrix uses that GLM call. And this is in the GLM detail namespace. That got included in common.h. The call is perspective, and perspective then takes the field of view, aspect ratio, near and far plane distance, and computes a projection matrix out of it. That is exactly the discussion that we had in lesson 2. Now, the reason that this is done not inside of the update, notice that the update call says update view matrix, and there's a update view matrix call, and it is independent of the update projection matrix call, is because the projection matrix probably updates infrequently. Certainly less frequently than the view matrix does. The view matrix needs to be updated typically once per frame because the position of the camera, the direction of the camera, where it's looking, those things change from frame to frame. And the projection matrix only changes if one of these 4 values changes. So those values change less frequently. It's still available in the public interface. If any of those values did change, then clearly you would call update projection matrix. Now, the update method, what the game class hits every time when it calls the component's update, is the update view matrix call. And if you recall, again from lesson 2, I said that the GLM library has a look at, or has the ability to construct a view matrix, and indeed this is it. So the look at specifies 3 arguments: the position of the camera, which way is up, that's the 3rd parameter, and then the target. Where am I looking in 3D space? What thing am I looking at? What vector? The direction vector is a unit vector, so it's 1 unit along the direction vector. It's position plus 1 unit along the direction. And that allows us to look straight ahead, so to speak. So wherever it's facing, go 1 unit along in that direction, and that's how we compute our view matrix. And we do this every frame. So that's a camera. I guess maybe one last piece here to discuss is the use of Euler angles and applying rotations. With Euler angles, we need 3 vectors to describe our orientation in 3D space. We have a direction vector and an up vector. Those are the first 2 things that we talked about in this camera there. So the direction vector is which way am I facing, the camera facing. Up is which way is up. And I said that the right vector is the cross product between those other two vectors. And if we want to transform, we want to rotate, this is not for translation, right, for the camera, that's just modifying the position. But if we wanted to rotate the camera around any axis, we can pass in a transformation matrix, a mat4. And that mat4, you would suspect, would be populated with rotation matrices. And what we'll do is then take the direction vector, null out the W components. So the direction vector is a vec3, but in order to transform it by a mat4 or a 4x4, the columns need to match the rows. So this needs to be a vec4, but remember this is a direction vector, so that fourth column, the W component, needs to be 0. So the translation would zero out, it wouldn't apply. Now what we'll do is then transform the direction vector, normalize it to make sure if there was any scale that happened to be sitting in that transform, it would go away. This would remain a unit vector. Do the exact same thing for the up vector, and then cross the up vector and the direction vector to compute the right vector. Now, the reason that we recross this, the next step you see there is m up equals cross and then right in direction again, is that the direction vector and the up vector, they didn't have to be orthogonal to begin with. But we want all three of these to be orthogonal. We want these to be orthonormal vectors, orthogonal to each other in unit length. So we cross the right in direction that we have just computed, the right with either the direction vector that you would cross with or the up vector that you would cross with to recompute the other. And that's just to guarantee that this indeed is a set of 3 orthonormal vectors. So now that we have our base class in hand, let's look at our first-person camera class, which changes this just a little bit. The first-person camera class extends this. It's the same underlying base code, so applying rotation is the same idea. But this time we're going to accept input from the mouse and the keyboard. And the mouse and the keyboard input we're going to accept is done inside of the update call. So we're going to override the game components update call. We're going to override initialize as well. And let's take a look at a little bit of how this is done. We've got a default mouse sensitivity, rotation rates, and movement rates. Those are all going to be used inside of update. The last cursor X and last cursor Y members, those members are there to track the relative position of the mouse. When GLFW gives us a position, it always gives us that position in absolute space. We want relative motion in order to get a first-person camera to behave like we want it to. So let's take a look. The implementation of this class looks like this. We initialize the base class first, and then we call GLFW get current position so that we get a base position for our last X and last Y. That's going to prime the pump, so to speak, for the mouse cursor. And then almost all of our code for this class is inside of the update call, right, if you notice that. So inside of the update call, remember we had seen the on-key call, or we can actually respond to events. Well, we can also poll keys. GLFW allows us to do both. It allows us to operate in either mode, in an event-driven mode for getting key presses, or in polling. And in this case, since I want to look at this data every frame, I'm going to poll the keys instead of waiting for an event to be processed. Likewise for the mouse. So the GLFW get key does exactly that. It polls the state of GLFW to say, is the GLFW key W pressed? That's the if statement there. It would return an enumeration, and the enumeration for pressed is the value 1. So that's why I can do an if statement that looks exactly like that. So if the W key is pressed, then I'm specifying the mouse movement Y. This is just a vector 2. It just stores 2 floating point values, and I'm going to zero them out. And if I'm going forward on the W, all I'm doing is specifying this as 1. And if I'm going backwards, it's -1. And if I'm strafing to the left with the A key, I'm specifying the horizontal component here, the X component, as negative along the X. And if I'm strafing to the right, then the horizontal component is going to be positive. I'm not using these values. This is an identity for multiplication. It's just flipping the signs. So which direction along the right vector for the X and along the direction vector for the Y is my movement going to be applied. So now I've just captured movement amount. And the next thing I'll do is capture rotation amount with the mouse position and buttons. So this time I'm going to get a GLFW cursor pause. So now I have, from the previous call, from the initialization, I have the last cursor pause, and now I have the current cursor pause in these temporary doubles for X and Y. And if the left mouse button is currently pressed, then what I'm going to do is calculate the relative amount of movement, which is the last cursor's X minus the current cursor's X, and the same for Y. And I'm going to multiply that by some gain, some mouse sensitivity. That's just a knob that you can dial in case you wanted more or less sensitivity. This is just an option you could supply inside of a menu screen. And then finally, when I'm done with that, then of course, then the last cursor X becomes the current cursor X, so the next time through this update cycle. So then we're going to grab the elapsed time. And this is the first time that we've used elapsed time, so I want to just spend a moment and discuss it. The reason that we care about things like the elapsed game time, and remember what that is, that's the amount of time that has elapsed between frames, is that that frame rate can fluctuate. And instead of our movement being dependent on how fast your frame rate runs, we want it to be dependent instead, not on the number of times the frame ran, but on a fixed time scale. We want to say, okay, given how fast that it takes to execute that one single frame, I'm going to apply that much value to the rotation of the mouse in this example. Or how much movement did I move? I want to make that time-based rather than frame count-based. So that's exactly what we're going to use this elapsed time value for. So with the elapsed time in hand, we're going to compute the rotation vector. And the rotation vector is simply the rotation amount that we've computed here. That's that relative amount in the mouse sensitivity, times a rotation rate, which is in degrees per second. And that M rotation rate, I'm specifying through a default rotation rate, or the end user can modify that with a rotation rate reference. So I think that default rotation rate right now is 1, so 1 degree per second, times the elapsed time. That produces a vector 2. Then I'm going to take that vector 2 in its y component. This is for pitch rotation. The y component is the up, down, the vertical motion of the mouse. I'm going to take that rotation vector and using the GLM rotate method, which comes from the GLM detail namespace, the GLM rotate method then takes that amount, how many degrees am I rotating, and what axis am I rotating around. In this case, I'm rotating around the camera's right vector. So however the camera is rotated, its right vector represents its pitch axis, and that's how I'm pitching. This mat4 parameter is kind of an interesting thing of the rotate methods in GLM. GLM allows us to concatenate matrices automatically. I don't want any other matrix automatically here, I just want the identity matrix. But notice that the next call I call rotate, I'm going to take the previously constructed rotation matrix, and I will concatenate the new rotation, which is yaw. So the yaw rotation is around the up vector in all cases, not the camera's up, but the actual up vector y, the y-axis. The reason I'm doing that is because I don't want longitudinal roll in this case. I always mean the y-axis. You can certainly change this if you wanted to have a camera that worked in space, for example, and you wanted a button that would longitudinally roll you, then clearly your rotation might then want to depend on the camera's up vector. I'm not doing that here. I'm fixing that and hard coding it so that it's always the y-axis. So finally, I call apply rotation to apply that concatenated rotation matrix that includes both pitch and yaw rotation to the camera. And then finally, we're going to apply the movement. And just like we did a rotation vector here, we're going to take the movement amount, which remember is just going to be a positive or a negative value for each of the x and y components, times the movement rate, which again is just a gain, allows me to specify, I think I've specified it at 10 here. So you can have more or less rotation depending on each frame. And elapsed time, right? So for each unit of movement there, how much time do I want to move in 1 second? How many units do I want to move in 1 second? I'm going to modulate that by the elapsed time to be frame rate independent. And I will strafe along the right vector by the amount of movement that I've got in the x component, on the horizontal component. And likewise for the forward direction, I will do movement.y. So that was the movement.y and movement.x correspond to the GLFW keys for W, S, A, and D. So A and D for strafing, W and S for forward and backwards. Okay, so that's the camera class. And just to reiterate how that works, so that's me moving those around with the WASD keys and the left button held down on the mouse and yawing and pitching. All right, so there's two last things that I want to talk about here very quickly. One is the grid class. So if we go to the library project and we look at grid.cpp and grid.h, grid.h is a reference grid. And we can change the color of the reference grid. You can pass in the color. It has a position, it has a size and scale that you can change. That size and scale dictates how big the thing should be and how many individual lines should be distributed uniformly within the grid. And that's all done inside of the initialize grid call. Whenever I set the scale or set the size, then I invoke initialize grid. And let's just take a look at this because this is another way for us to look at rendering in 3D. I'm using a different vertex and pixel shader this time around, but they're actually the same thing as we did before. Let me pull them up. So that's the basic effect frag that I've stored in the library project, but it's the same fragment shader that you've just seen for our cube, and the same vertex shader that you've just seen for our cube. So inside of our grid.cpp file, those are the shaders that we're using to build our shader program. We're initializing our grid. I'm not going to walk through this code, but just trust me when I tell you, or just walk through that code yourself to see that this produces a uniform grid of lines. And then finally, when we draw this code, we're going to do GL bind vertex to take the initialized vertex array object. It's not indexed in this case, so there's no elements that we're binding here, no index buffer that we're binding. And this time around, we're using GL lines, and that's what I really wanted to talk about. I've got this GL lines for GL draw arrays. We've now looked at GL points, GL triangles, and GL lines. And GL line specifies I want to draw lines, and how many vertices for each line segment do I want to use? And the vertex gets produced there inside of the initialized grid call. So the end result is whenever inside of my rendering game.cpp file, I specify a grid, and I can specify, in this case, I'm using the default size and default scale and color. I can specify different sizes and scales and colors, but then that produces for me a nice little reference grid that you can use from that point forward. Okay. The very last thing that I want to do is just spice this up a bit and make the cube spin. So if you go back to our cubedemo.h, what I want to do is override, not draw, I already got that overridden, but now update. From this declaration, let's hop over to cubedemo.cpp. So somewhere before the cubedemo draw method, let's start by typing in cubedemo update and const game time. I'll have a game time object. And now let's look at something. We want this to rotate at a particular rate, and I had got this little rotation rate static float here, this GL float object. And we can specify that to anything. This is going to be, I'm going to default to 180 degrees per second. And what we can do is do code like this, static GL float angle, and let's default this to say 0.0f. Each time through this game loop, we just want the angle to be incremented by some amount. And remember, I want this to be frame rate independent. So let's static cast this to a float, the game time dot elapsed time. I'm going to multiply that by the rotation rate. Just that simple. I'm going to add this angle each time through the update loop, initializing it to 0 the first time through. And then what we'll do is use the rotate command for GLM. And what I'm going to do is build up the world matrix. So M world matrix, remember we had declared the world matrix here as well. But the world matrix up to this point has just been the identity. Now we're actually going to make it something, and it's going to be a rotation matrix around the y-axis. So we'll use the GLM rotate method. We're going to specify an empty mat4, which is the same thing as saying the identity matrix. We're going to specify our angle. And then I'm going to use vect3 helper up to specify the y-axis. So what this has done then is each time through the update loop, we're just going to apply a little bit of rotation. And now if we run this, we're going to see a rotating cube. And there you have it. And that rotates at the rotation rate that we specified, independent of the actual frame rate. So that about does it for this lesson. The focus of this lesson was to pass uniform data to shaders. So we took our cube demo and we created an indexed cube. So we introduced the new concept of an index buffer. And then we took a world matrix and the view projection matrix from the camera, concatenated those two together, passed those in as a uniform matrix called world view projection to the vertex shader. And then we wrapped it up with a look at camera and first person camera classes and the grid class.